All right, so after some hopefully thoroughly enough discussion on the whole concept of continuity of a function as far as how a function can be generally continuous throughout its own domain, then we're going to take that and apply that into understanding the intermediate value theorem. So the intermediate value theorem here came out as a consequence of a function being continuous. And so before really writing down the worded theorem here, allow me to actually demonstrate the idea of the intermediate value theorem through a graphical explanation first. So all right, so now at this point, once we are all fluent in terms of what it means by being a continuous function, then let's say the whole idea now, and we don't need to bring too much about the limits into this, but just like how any of us has been understanding continuous means when we're drawing the graph of the function, we have to be able to maintain a drawing without lifting our pencil. And so let's say here's some portion of the graph of some function f of x, and the portion here is being done between, I'm going to restrict the graph of the function in between an interval from a to b. And so outside of the interval, I'm not too worried about what's going on outside of this interval. I'm not too worried, but at least for this function, it has to be continuous inside of this closed interval from a and ending at b. And another thing is that notice the way how I drew my interval and the way how I drew my picture here, and it doesn't have to be any particular function like is that an x squared, is that an x cubed. It's not something to be worried about, but generally we need our function to be continuous inside of this function, waving up, waving down. But the next important requirements here is that at the left endpoint here and the right endpoint here, these heights here, let's say we want them. We need those two outputs at the two endpoints to be different value. And keep in mind, all I'm saying here is that the requirements here, we want f of a is being different value, being different than f of b. But we don't necessarily need f of a to be lower f of b or f of a to be higher than f of b. It's not the key requirements here. But so basically that's what we need. The function has to maintain its continuity inside of this interval, and the function output at the two endpoints needs to be different value from each other. And so now, if we have this satisfied, meaning the function output at A is other than the function output at B, then think about in terms of the vertical y-axis, then whichever the lower value between FA and F of B right here, whichever the lower value that is the beginning of the interval on the vertical axis. So right here, f of a is based right out from my picture, then f of a is lower value. So it's the beginning of an interval on the vertical axis, and f of b in this picture being higher value. So it gives the end of the interval on the vertical axis. And so now on the vertical axis, I have for myself a vertical interval between f of a and f of b. And so now the idea now is that the whole idea of the intermediate value theorem is that if we now pick any value n being inside of this vertical interval, so n is a value being anywhere inside of this vertical interval, then we have to be able to find, so think about if n is a value right here, then that means the height here becomes a horizontal line through. And so if we draw a horizontal line through that height n right here, then the line must cross the graph of our function f of x at a point. And that point is a value c being guaranteed inside of this interval. And so this is the whole picture of the whole graphical explanation of the intermediate value theorem. So let's formulate the whole idea into the actual worded version of the theorem. And so the intermediate value theorem now start out with saying let f of x, any f of x function, be a continuous function, or precisely let f of x be a function, but more precisely continuous on the interval closed interval. And remind yourself from our algebra concept, we understand that we use square brackets to indicate it's a closed interval. So this is the interval on the x-axis as we have seen earlier in the picture. And so f of x must be, first requirement, be a function that's continuous, at least on this closed interval, where furthermore the function output value at a at the left end is different value than the function output value at the right end. So that's the first two requirements as I was indicating in the picture. And so after having those given conditions, then the next thing we're having now, the real essential part of the theorem now is saying if the value n is a value between f of a and f of b. So this is the third further requirements. If we picked n, let's quickly swing back to my picture on the other board there, and you're going to find out again. So f of a and f of b, in my earlier graphical explanation, this is creating a vertical interval on the vertical axis. So if n here is a value that we can randomly pick anywhere between this vertical interval, and that's how the wording description is saying. And so if n is a value anywhere between fa and fb, then there must be a value c being inside. Now for the first time in this quarter, for the first time maybe for anyone viewing this video, but I'm introducing this symbol. It's a sideways cup with a little dash in between. But this symbol means it could be the first time any viewer seeing this symbol, but this means being inside. And so C here is a value C being inside, in between or inside the interval from A to B. Satisfying what we've seen earlier in the picture now. So f of c has to equal the value n. So that's the worded description of that. And so once again, back in my picture over here, so as long as we can guarantee that our function is being continuous inside of the interval here, then with any value n starting out being inside of the vertical interval, the interval on the vertical axis, then it is guaranteed. The theorem is a way to guarantee for us that we can definitely be able to find a value. Now, don't get me wrong on this. The theorem never said exactly where the value c has to be inside of this horizontal interval on the x-axis. The theorem only guarantees that we should be able to definitely find a value c somewhere inside of the interval on a horizontal x-axis that satisfied, see, the c value inside of this is hitting to that height. So this height right here is f of c, but the theorem says it should equal to the value n. You see how the height is being exactly meeting with that horizontal height, this height right here, horizontally at the y equals n. Okay, and that is the reason how we've had that we can always find a value inside of C of that horizontal interval satisfying that f of c equals n. And so this is how the intermediate value theorem is being worded. And so intermediate value theorem commonly is being referred to as an, I use this in a shorthand notation as well, but a lot of time mathematicians refer to the intermediate value theorem as, for short, the IVT. It's just for convenience of naming things. And so intermediate value theorem is being short as IVT. All right, and so I am now about to bring up an example to demonstrate how useful this theorem is. But at this point, I have to admit, anyone viewing this video, this particular video is quite early in your learning of calculus. So the example I'm bringing up here is not too useful, I have to admit. But when we progress through the course, and there will be later times, I should be able to bring back how we can apply the intermediate value theorem, and there at the later time you're going to see how a much better application, much better usefulness of this theorem. So the example we're about to do here is quite direct from this, but it's not as useful in your daily application for calculus yet. So I have to admit that, but like I said, just be patient and bear with me here. All right, so before I actually bring up the example, let's have a look at the following equation. For x cubed minus 6x squared plus 3x minus 2 equals 0. So it's an equation. It has unknown, and this equation here, at first sight, this is a cubic in a sense that the degree of this equation is up to power 3, degree 3 right here. And so we have learned. So for now, let's put this equation aside right here. If anyone is asking us to solve, let's say 5x plus 1 equals 0. If anyone is asking us to solve this equation for x, this is easy. I mean, x equals subtract 1 to the other side, and dividing both sides by 5, we get the answer easily. This equation was referred to as linear equation, and we don't need calculus to know this equation, to know how to solve this equation, and yes, the answer can be found easily. And then as we advance a little further into algebra, if anyone bringing up an equation like this for us, say x squared minus 4x plus 4 equals 0, for example, and ask us to solve this equation for x again. And like I said, as we advance throughout the course in algebra, then I'm sure any one of you have seen this equation. It's a quadratic in the sense that the equation here involves a quadratic term, power 2 right here. And so solving this equation has once again a definite method to solve. We can either use the famous quadratic formula, or we got factoring method, or we got grouping, and all over. And so the answer here, now allow me to skip how we solve these things. This is, anyone viewing this video should be able to expect the answer for this. Plus and minus 2. We got 2 solutions. But now when we step outside of linear and quadratic equation and start getting into cubic like this, none of our algebra courses before has introduced a solid method to solve this. Maybe a couple problem, but very limited, and we never had, and trust me on this, we never had a clear and definite answer or a clear and definite way to solve an equation like that. And so now I'm bringing up this equation. I'm not asking any of my viewer here to solve this equation. It's still such a nightmare. Even I can't do it. But at least this is what we can do. So I have to make clear, we are giving up the idea about solving this for x. But we know, let's say we know that it's going to have some solution. So in this example 1, this is what I'm doing. And this is actually the only example we need to see here. So I'm not going to call it example 1 because there won't be an example 2. But this equation, I'm going to show that this equation has a solution. And solution, remind yourself, this kind of equation, the left-hand side is a polynomial. So famous name for a solution to a polynomial equation. Many professors also refer to as 0. So this, we want to show that this equation has a solution in between, or that's not accurate way of writing it. How about between 1 and 2. So that's our goal. And once again, I spend quite a good amount of time explaining that I'm not attempting to solve this equation because nobody really not too many people know a definite way to solve a cubic. And trust me, when these polynomial equations become even higher power, then it's even such a nightmare of solving these things. So the best thing we can do here is we only want to show that this particular equation has a solution. And showing means we want to guarantee that this equation has a solution. But that solution here is being inside of this interval. So what I need anyone viewing this video to understand is that this is an interval on the x-axis. Because see, it makes sense with the problem we're doing here is that the value we're solving for, the value here is the value for x. So it should be on the x-axis. All right, but so after so much beating around the bush, let's get to it. How I see the intermediate value theorem can be applied in here is that now this could be the first time, or this could be the many times I'm reminding anyone viewing this video about this fundamental understanding about any equation. But see, your equation here, the truth about any equation is that left-hand side 4x cubed minus 6x squared plus 3x minus 2. Left-hand side can be regarded as a function. So any equation, you can always regard the left-hand side as some function that involves some function of the designated variable, input variable here. So here I can regard my left-hand side as the function f of x equals 4x cubed minus 6x squared plus 3x minus 2. And the right-hand side, we can regard to that as a value. And so the truth about this equation is that we want to find the value for x such that this function has an output equals 0. So now here's how the intermediate value theorem or the IVP is starting to come in place here and become useful for us. But first thing, it's a polynomial. Your f of x came out right from the left-hand side here is a polynomial. And so we've learned from our concept of continuity. And after our conclusions we've made, after the earlier lecture about continuity, then any polynomial is a continuous function. And so in that way, one thing I know for sure. So what we already knew as Just the way it is for these functions. What we knew already is that this function f of x is continuous on the closed interval from 1 to 2. So let's quickly flash back at the beginning description of our problem. But see, those two given values right here, they are now acting as left end and right end on your x-axis. So your x-axis runs infinitely, extending on two sides here. So 1 could be here somewhere and 2 is there. So now I'm having a closed interval. A closed interval starting at 2 and starting at 1 and ending at 2. Okay? But now I want to show that this problem, this equation will have a solution right inside of this. And another reminder about the truth of a graphical understanding about the root of any equation or the solution of any equation here. Any equation here, see, we call it, it's a zero. It means when we draw the graph, it has to cross the x-axis. And so now we want to show that the graph for f of x here, the graph for our function f of x, has to cross the x-axis at some point inside of that interval between 1 and 2. And so keep that image in your mind as we progress along. And so now getting back on my other board here. So first thing we know, because I'm making my steps here and build it up, how we can apply the IVT, the intermediate value theorem. So f of x is now known to be continuous between 1 and 2, anywhere inside of that closed interval. And further, let's consider further. Let's find out what's the function output value on the left end of our interval. So calculation comes out to be -1 for f of 1 and f of 2. Calculation came out to be 12 for f of 2. And so clearly speaking, f of 1 being -1 is different value than f of 2, the output at the right end point on our designated interval. And so now that's the next factor here. And notice even a little further, f of 1 equals -1 and f of 2 equals 12. This value here is a negative value, but this output value for the right end point of our interval here is a positive value. So that means now I have to erase part of my other board right there to make more space for myself. But now between 1 and 2. But so imagine that here's now I'm going to putting up my vertical axis, the y-axis. The x-axis is here. 1 is a value here somewhere. It gives me, so 1, it gives me some value -1. A value -1. And then at x equals 2, it gives me some output value being positive 12. So let's say, of course, forgive me if I'm way out of scale, but it's completely okay. That's not the point of the problem here, but our function is continuous. And you see now I'm going to make that demonstration by drawing the graph here, but being a continuous piece of graph inside of this, then the only way for being continuous inside of this interval from 1 to 2 is that our function has to cross the x-axis somewhere, because here 0 is a value between somewhere, and this is our n value right here. That's how I see that to be consistent with the intermediate value theorem. And so now treating n as a value between that vertical interval, then the only way for this function this continuous function to maintain its continuity inside of this closed interval is that it has to hit. So at some point C here between 1 and 2, our closed interval on the x-axis, we have to have some point, some value C inside of this closed interval that guarantees our function output value to equals this value n equals 0, being exactly inside of the vertical interval from -1 to 12. And I remind you again, being between -1 to 12, these are the two output values created by the two endpoints of our function right out from the closed interval 1 and 2. And so now, so looking back at this, after the two requirements here being satisfied, and then with that quick little demonstration, then now I'm going to move on with the next step right here. So, and I hope you have been taking notes along, because I need to erase this. And so what I recognize now, and earlier was only a graphical explanation. And so now I'm going to say since n equals 0. And why do I look at 0? Because 0 here, we can regard to that as the output value that we equate our function on the right-hand side right here. So since n equals 0 is a value is somewhere inside between -1, anywhere between -1 and 12. See, so this is the vertical interval that I was talking about in my earlier picture. So I really have to apologize for switching back and forth between the boards, but we need to a lot of time look back and forth to see the picture here. But see, -1, the output on the left end point of our interval, and 12 is the output value for our right end point. Okay, and so n equals 0, and as I pointed out graphically earlier, that n equals 0 is a value vertically between -1 and 12, and that's why I'm making this statement here. So since n, sort of like being chosen, is inside of this interval, then so now IVT guarantee that there must be a value C being inside of the interval from 1 to 2 that satisfying f of C equals 0. And so now, hey, wait a minute, but f of C equals 0. F of C equals 0 is the solution. This is the solution. This is the solution. So that means I should have drawn my arrow the other way. That means C is a solution inside of the interval from 1 to 2. And that is how, now back to our beginning, our ultimate purpose of this example right from the beginning. I only want to say that, I only want to show, meaning coming up with a way to guarantee that this equation has a solution between, and that solution is famously known as a 0. See, that's where the graph is crossing the x-axis. That's why it's called 0, 0. So we only need to guarantee there's a solution between the interval, anywhere inside of this interval from 1 to 2. And there we go. We have made our conclusion. And so as soon as now the intermediate value theorem just now guarantee for us that there must be a value C inside of that. And this value here satisfying the function substituted C equals 0. But this f of C equals 0 is nothing but 4c cubed minus 6c squared plus 3c minus 2 equals 0. Or in other words, C is the value that's making the left-hand side equal the right-hand side on our equation. And that is why I can now legally say that C is a solution being inside of this interval from 1 to 2. All right. And so now, if we're looking back, and at this point, we're actually done with our proof. We're done with this particular example. And then that's this big little shaded square right here is sort of like a huge period indicating we're done, and this is the end of the proof right here. And so quickly, let me mention one more important thing, sort of useful in this IVT intermediate value theorem as well. Now, I'm not going to waste your time watching me to rewrite the entire worded statements of our theorem earlier, but I do need to write down this very last statement so anyone can, so it can catch your attention, and I'm pretty sure that was how you took notes earlier. But the very final statement say, if n is a value between f of a and f of b, then there must, allow me to skip that word then the whole time, but that's the whole idea of these if-then statements. So if we're starting out with this known condition, n is a value anywhere between fa and fb, then there must be, so there must be a value. But now allow me to underline, we wrote it down earlier, but you know, nothing to be emphasized much rather other than seeing an example. But now I do need to underline this word. There must be a value, c, being inside of the interval from a to b, anywhere in between a and b, satisfying f of c equals n. So all that's the very final statement. This is how it looks back in the intermediate value theorem. But so why do I particularly underline this term a here? Because here's the usefulness of that. This theorem, once it guarantees, if the theorem can guarantee for you a value c inside of this interval, that means there could be another one, and there could be another one, or in other words, there must be a value, in other way of thinking, there must be at least one solution c being inside of this interval from a to b that satisfies this equation f of c equals n. And that's the usefulness of that. But remind yourself again, and I did that in my example earlier, that I never attempted to find what the actual value of c is. That we cannot find that. It's not and it's not even the goal of the problem. The problem here is we just want to guarantee that there is a solution inside of the designated interval, and that's all there is. And so sadly, this is at this level of any of your learning for viewers for this video lecture, and this is the only application I can bring it out here that's about the closest to your level of math that you at when you're viewing this video. But believe me, as we progress through the quarter, and then when we hit to other important concepts, and then there will be points, there will be times later on that I should be able to bring back this intermediate value theorem and apply it into the other places there, so that you can see much more the usefulness of this theorem out there.